All right, everybody, welcome back. So in this video, we're going to continue with our bonding theories. We're going to talk about valence bond theory and then hybrid orbital theory. It just gives us an explanation for why we do observe certain shapes that we do based on the orbitals available to bond. And then we get to talk about overall polarity of a molecule. So this is valence bond theory here, and this is very basic. This is based on the electrons that are coming from their atomic orbitals and overlap of those orbitals. So let's just break it down first by looking at hydrogen and fluorine. Hydrogen, we know its outer electron that's going to be used for bonding is a 1s1 electron. So that's in a 1s orbital, that's a sphere. A fluorine has an electron configuration of helium, 2s2, and then 2p5. So it has one unpaired p electron, and that's going to overlap with the hydrogen and share its one electron with the unpaired one of the hydrogen. So that's what it looks like. You basically take one of the p's that can line up and overlap with the hydrogen. This overlap here represents your bond. Sometimes you see it with two dots showing the two electrons overlapping, similar to as you would draw a Lewis dot structure. Sometimes you see two arrows overlapping or paired, so you can show that there is a bond. Okay, if, for example, you had two fluorines, then the two available atomic orbitals to overlap would also be a 2p. If we had this as the x-axis, that would be the 2px's for each of them, and you just overlap the lobes. That's giving that bonding there. So that's all there is to valence bond theory. You're using those valence orbitals to explain the bond. So that can be very useful and adequate for very simple molecules. However, there are some cases where it really doesn't explain some of the shape that we see for others. So for example, methane here. We know from Vesper theory that this is tetrahedral. It has four groups. That means there are four orbitals to bond these H's. But what did we learn about tetrahedral? It's perfectly symmetric. It's a tetrahedron. And all of those bond angles are 109.5. So if we try to apply valence bond theory to this, it wouldn't work because you would have used the S's for H's, that's fine. But for carbon, what are the outer electrons to use? You would have not the 1s2, not the helium part, but you would use the 2s2 and the 2p2. So if you use two s's to overlap and two p's, you would not get a perfectly symmetric molecule. So what chemists came up with to explain this is these orbitals actually do some sort of mixing. We call that hybridization to give us, and if we started with 4, we end up with 4. So we start with 4 atomic orbitals, we'll mix them and we'll get 4 new, what are called hybrid orbitals. Since we're going to mix 1s and 3p orbitals, we call those sp3 orbitals. And those 4 electrons can now go in those 4 orbitals that will bond to each of the hydrogens, each of those 4 hydrogens, allowing for that perfectly symmetric tetrahedral shape. So I can visually show this, an S and 3 P's will mix and hybridize to give us these 4 perfectly symmetric sp3 orbitals. So instead of looking like these and overlapping these individually with the H's, what it looks like is this: a smaller lobe on one side. Here's a node. This is where the center of the carbon would be, and then a larger lobe. And you would be overlapping the larger lobe here with an H. So this large lobe here is what you see here, each of these green lobes. And do you see how there are 4 carbon's in the center, and carbon has those 4 to bond with each of the 4 hydrogens. And if you just took a spherical S, you can overlap here. And that overlap, you can represent it with 2 dots or just some shading. That is your carbon-hydrogen bond. Okay, just what you really need to know is to get something tetrahedral, you needed to form 4 new hybrid orbitals. So that'll come from blending an S and 3 Ps. If you want to make something to form a trigonal planar shape, you need 3 new hybrid orbitals. So that'll come from an S and 2 Ps. So notice that the new hybrid orbitals you need to make, those numbers, is 1 higher than this number here for the P. A linear geometry will require an S and a P to combine. So what I need you to know are these 3. If you combine an S, 3 Ps, and a D, you get 5 for trigonal bipyramidal. Add another D and blend those, you get 6 for octahedral. I already mentioned what I call conservation of orbitals. The number of atomic orbitals combined equals the number of new hybrid orbitals. So if you have an S plus a P, you get 3 sp2 orbitals. And that's important for that trigonal planar shape that has 3 electronic groups. So this is just really something to memorize. Anytime you know something that has a linear orbital geometry, you know it's sp hybridized. So just to make it clear, hybridization is related to the orbital geometry, or you could just think of it as the number of electronic groups around the central atom. Just a reminder, 1 lone pair or an atom counts as 1 electronic group. So let's look at this situation. What if we talked about water? Water has how many groups? 2 lone pairs, 2 H's, so a total of 4 groups. So it has an overall tetrahedral electronic arrangement. It needs 4 balloons or 4 orbitals. So I need to have this tetrahedral arrangement. That means those hybrid orbitals will come from an S and 3 Ps. So O is sp3 hybridized. That's how we say it. It's sp3 hybridized, or you could say it uses sp3 hybrid orbitals for bonding. So just a snapshot of what I just discussed. Something that's di-substituted or linear, like this. X is the central atom, Y's are other atoms. This is shown in this example here, acetylene, and your X is carbon. And it's bonded to another C and an H in this case. That's linear. No lone pairs around the central atom, so this is sp hybridized. This carbon is sp hybridized. So notice, in this case, I had 2 central atoms. Just focus on 1. If you want to do the other one, you could see also it's the same. Bonded to an H and a C, no lone pairs, also sp hybridized. Something that's trigonal planar or tri-substituted and no lone pairs, as in ethylene, shown here. This carbon then is sp2 hybridized. The carbon itself, we call it sp2 hybridized. So you only give this hybridization to the central atom. Since this had 2 central atoms, then I could go over here and look, oh, this is also trigonal planar, so it's sp2 hybridized. Go to something tetrasubstituted, no lone pairs, like methane, this carbon, sp3 hybridized. So that's just something that you want to know, memorize, however you want to do it. Okay, let's talk about actual bonds, so single and double or triple bonds. All single bonds are also called sigma bonds, given this symbol. You can get a sigma bond when you have direct head-to-head overlap. So I've already shown hydrogen can have 2 S's overlap, or a S and a P, like HF, or FF, fluorine. You can have 2 P's overlap here. I'm sorry, 2 F's overlap here, and they're P orbitals overlapping specifically. A pi bond is different. And a pi bond is actually the second or third bond in a double or triple bond. So let me say that again. In a double bond, you have two bonds. The first one will always be a sigma bond. It's the second one that will be a pi bond. Or if you have a triple bond, the second and third one will be a pi bond. How is a pi bond different? You have a node in the center. So here, if we're saying this is the x-axis, the p-axis can overlap head to head. But say you have like pz, maybe this is the z direction. So then there's a node in the center. They can't overlap throughout, so they overlap a little on the top and a little on the bottom. Even though they overlap a little on the top and bottom, it's still one pi bond. And it's hard to draw sometimes, so we kind of just give it a cloud above and below this nodal plane. Let me go through 3 examples. This is ethane here, C2H6. I could draw it like this, and I just give some other info on bond angles, but it's tetrahedral. Since this is only a single bond, it's a sigma bond, and sigma bonds have that direct head-to-head overlap, so there's free rotation around that bond. Think of this as a propeller. You could spin this around and around, this side too. There's always energy where the molecules are bending, stretching, rotating, that sort of space, rotating in space or spinning around bonds. Notice we use a dash and wedge to show that 3D shape. I can show this as the sp3 orbitals overlapping here. That's your sigma bond right here. Also, the overlap with the H's, the C's and H's are also sigma bonds. And all the yellow, those 4 yellow orbitals around each carbon, those are the sp3 hybrid orbitals. sp3 because it's tetrahedral geometry. When we go to ethylene, that has a carbon-carbon double bond. So this has a pi bond where you have overlap above and below. It's still just one pi bond. The sigma bond is that first single bond, gray one shown here. Since this is trigonal planar, it is sp2 hybridized. And because the pi bond is above and below the nodal plane, there is no rotation around this bond here. Think of it as like 2 ropes or 2 chains or 2 arms connected. You can't spin around and around and around here. In acetylene, this is used in blowtorches because you can burn it at a high temp. It's linear. So this carbon here is sp hybridized, and it's the other one is as well, and you can have this gray overlap here. This is the sp overlap, and that's your single or sigma bond. The 2 other bonds, the second and the third, will be your pi bond. So you could think of these 2 blue PZs overlapping above and below, or these 2 yellow PYs overlapping. Okay, so that's it for the bonding theory. What I want to just end with is overall polarity. What's good is you guys are or have already done the lab on polarity, so that'll help a lot. You already know about bond polarity. If something's more electronegative, it's going to pull on those electrons more. It's a tug of war. So whoever's pulling more, it's more partial negative, and the other guy's partial positive. But what about a whole molecule? In that case, you also have to look at shape. So if we look at carbon dioxide, there's definitely a dipole going towards the more electronegative O. But because the shape is linear, those dipoles, which are actual vectors with magnitudes that you have or will measure in your lab, those are in the complete opposite directions. They're pulling evenly on each other, so they cancel out. So the overall dipole is none, and we call that molecule nonpolar. However, in water, we do have bond dipoles. The difference here is that because of the lone pairs, this is overall bent. So you can also think about dipoles going towards the lone pairs. Overall, you have this dipole, as I've drawn it, a net dipole for the molecule going in the up direction. So there is an overall dipole for the molecule, so we call it polar. So just be very careful. Anytime, for sure, if you have lone pairs on one side, you have polarity to the molecule, because you can never completely balance out the lone pairs if there are atoms there. We use dipole moment, which is given mu, to basically represent the net molecular polarity. So let me give you an example. Here in ammonia, we know there's a lone pair. There's an overall net dipole going up. This can be measured in Debye units, 1.47. So ammonia is polar. There are some that are more polar, like water is a little bit more polar. It has a more electronegative O and 2 lone pairs. If you look at CCl4, carbon tetrachloride, each of these has bond dipoles because chlorine is more electronegative than carbon. It'll result in a dipole. But look at the shape. 4 groups around carbon, tetrahedral, perfectly symmetric. So it may not look perfectly symmetric to you, but it is. Think about 4 identical twins, or I don't know what that word is, quadruplets, pulling evenly on a rope. No one's going to win out over the other person. So overall, the dipoles cancel and the net dipole is 0, nonpolar. So again, you're looking at bond polarity and shape to determine polarity of a whole molecule. If you just have a bond, yes, if there's one significantly more electronegative, that molecule will be polar. If you're looking at a whole molecule like methane, and in this case, this is carbon tetrachloride, these are perfectly symmetric and all the atoms are identical. So you have the identical dipole. Those will cancel. But look at this example. If I have 3 H's and 1 chlorine in a tetrahedron, that chlorine is going to pull, in this case, up, but there is no bond dipole for carbons and H's because the difference in electronegativity is negligible. So there is overall polarity. So even if one atom is pulling stronger than the other, it can make it polar. We already went over ammonia. Here, BF3 is trigonal planar, so it's perfectly symmetric, and all of the fluorines, even though they have a dipole with the boron, they're going to all evenly pull. So again, now we have identical triplets, and they're all pulling evenly, so no net dipole, overall nonpolar. One tip I want to give you before I end here is anytime you have something asymmetric, meaning lone pairs on one side and atoms on the other, as in all these cases, that will always be polar. So you can think of a polar bear being asymmetric, and a polar bear is asymmetric. It's got a head end and a butt end. If you swap those, that's different. It's symmetric through the length of the body, but still it's got a head and a butt. So polar bear is asymmetric. Anything that is asymmetric will be polar. Okay, that's where I'm going to end today.